My name is Mitch Clement. I'm from the University of Colorado Center for Advanced Decision Support for Water and Environmental Systems, or CADS West. I'm going to be talking about the use of RiverWare for multi-objective river system management and hydropower planning. And I also want to acknowledge Dr. Edie Zagona, who is the director of CADS West and has been the head of the RiverWare project since its beginning in the early 1990s. So RiverWare is a general river and reservoir hydro policy modeling tool developed at CADS West. It has been developed collaboratively together with our three sponsors, the Tennessee Valley Authority, the U.S. Bureau of Reclamation, and the U.S. Army Corps of Engineers. So it has been a collaborative effort both in the development of the software tool itself with these sponsors in CADS West, and then the tool has been used for collaborative management of river basins throughout the country. So I'm going to be talking about RiverWare's two multi-objective solvers, which are rule-based simulation and optimization, which uses a preemptive linear goal program. And I'll talk about these in the context of two applications, rule-based simulation for long-term planning and policy analysis in the Colorado River and hydropower optimization in the Columbia River Basin. Just some general RiverWare information. You construct a model in RiverWare by linking objects that are selected off of a palette. The objects represent features of the basin, such as reservoirs and reaches. And then those objects are customized by the user by selecting physical process methods or computational algorithms. So for example, if you're modeling hydropower, you have roughly a dozen different algorithms to choose from and how power is calculated in the model. Similarly, in reaches, you can model routing with either a simple time lag or anything like a hydraulic routing method such as kinematic wave. You can also optionally model water quality. The time step sizes in RiverWare range from 5 minutes up to 1 year. So much of the power in RiverWare actually comes in the representation of policy in the model. And whenever you're talking about multi-objective modeling, you have to consider how are you going to trade off those competing objectives. And in RiverWare, that is done in a prioritized manner. So in rule-based simulation, the first solution approach I'll talk about, the policy is expressed as a prioritized set of rules in the model, where the rules have a general form of, if the state of the system is such, then set some decision variables. So a very basic rule might say, if a reservoir outflow is currently below some specified minimum, then increase it to the minimum. So the rule is going to assign values to variables such as reservoir releases or diversions, and then that allows objects to solve for the effects of that rule, solve for variables such as this reservoir storage, pool elevation, power generation, and so on. And then it'll go on and execute higher priority rules, which can overwrite the effects of the lower priority rules if necessary. So one key to the policy modeling in RiverWare is the RiverWare policy language, which is a rich programming language developed within RiverWare for modeling basin operating policies. The policy language uses a graphical syntax-directed editor where it has knowledge about what are legal syntactical expressions that can be added based on the use of a palette to guide the building up of those policy expressions. It also comes with a built-in library of over 200 predefined functions, as well as the ability to create user-defined functions. And the policy language was really developed with three primary goals in mind for the purpose of facilitating that collaborative use of the model in basin management. And those goals are, first, to be able to express any complex operating policy. It provides very large flexibility to be able to express any unique basin operating policy. You're not locked into any single policy structure. But with that flexibility, we also want the policy to be easy to read and understand. And so part of that is the use of user-defined functions, where you can compartmentalize complex logic within a function, give that a meaningful name. So then at the top rule level, you can easily read conceptually what the policy logic is doing, which variables it's setting. And then another real key is that it's easy to change the policy. So the idea here is that the policy is formulated at the model level in the user interface. So actual water managers and stakeholders can come in and edit the policy, modify it as needed without needing to be a software engineer that's going into the hardwired code of the model to change the policy. So the first application makes use of rule-based simulation, and that's the Colorado River Basin, which is in the southwestern portion of the United States and parts of Mexico. And the basin covers portions of 7 states in the US and then Mexico as well. Just a quick overview of the basin. Most of the precipitation comes in the upper portion of the basin in the form of snowfall in the Rocky Mountains. And then in the middle portion of the basin, there are 2 large reservoirs that provide most of the storage, also very large hydropower capacity at those reservoirs, Lake Powell and Lake Mead. And then most of the consumption takes place in the lower portion of the basin where it's very hot, very arid. There's critical agricultural regions there that are using basin water for irrigation, as well as major metropolitan areas, including Los Angeles, San Diego, Las Vegas, and Phoenix that are making use of basin water. And then as the river travels on into Mexico, for many decades, the water never actually reached the Gulf of California before it was used up. So it left basically an ecological disaster in the Delta. So along with the challenges of managing a basin that spans multiple states and 2 countries, the hydrology is also very challenging in the basin. So it's highly variable. Currently, we're in the midst of a 20-year drought of record, and it's also non-stationary. And so going forward, with climate change, there's a wide range of uncertainty looking out towards the future, looking at the hydrology. And then along with that, in terms of the demands, you can see from the red curve over the past century, they've been steadily increasing to the point now they outpace the supply. So, and also along with demands increasing, there's wide uncertainty in demands going forward into the future. So that creates significant challenges in planning and management of the basin. So just a quick history of some of the management of the basin. It's operated based on a complex set of compacts, treaties, legislative laws, and court decisions that collectively comprise what is known as the law of the river, which prescribes how all of the water must be allocated and tracked. For most of the 20th century, the Bureau of Reclamation has taken a very top-down approach to management of the basin, really making unilateral decisions on basin management. This has resulted in a lot of feelings of animosity from the water users towards the Bureau of Reclamation. It's resulted in numerous lawsuits, and so really an atmosphere of contention in terms of the basin management. But in the 1990s, there was a significant shift at the Bureau of Reclamation away from this top-down approach towards more of a collaborative approach to management, where now the stakeholders began to take an active role in the decision-making process in the basin. So with that move towards collaborative management, it also required some new tools to be able to facilitate that stakeholder participation in the decision-making. And that's where Reclamation's involvement with CADS-WES and the development of RiverWare came into play, and specifically the Colorado River Simulation System, which is Reclamation's long-term planning model developed in RiverWare. This is a relatively large model that covers the entire basin, includes 12 reservoirs, over 500 water users in the model. It solves at a monthly time step using the rule-based simulation solver. And with those rules, it is able to completely represent that complex law of the river. But not just that, a real key is that with the model, all of the stakeholders actually have access to the model and can run the model themselves and do their own analysis and test their own policy alternatives that they want to try within the model. And that's been a key component in some landmark agreements over the last couple of decades in terms of how the basin is managed. So beginning in 2007, when the 7 basin states came together for the first time for really a revolutionary agreement in terms of how they were going to manage shortages in the basin over the next couple of decades. And the model played a key role in terms of having a common modeling platform to inform those negotiations. And then in 2012, Reclamation completed a major supply and demand study where they're looking out at different climate scenarios 50 years into the future, analyzing hydrologic scenarios, demand scenarios, running over 100,000 simulations. And a key piece of this, again, was the stakeholder participation in providing policy alternatives that they recommended to run through the model and evaluate based on the specified performance criteria. And then Mexico also uses the model now, and that has been able to provide them with information for negotiations to updates with the treaty between the US and Mexico, where now Mexico has become more of an active participant in management of the basin, sharing in surpluses and shortages. It's led to agreements that now have provided environmental flow pulses that allow water to flow all the way to the delta in recent years. So really the key here, the model providing that common platform for analysis among all stakeholders to bring to those negotiations has been critical. So I'm going to shift gears a little bit now and talk about the other multi-objective solver, RiverWare optimization, which uses a preemptive linear goal programming solution. So just a little bit about the individual components of that. At the core, the solution engine of the solver is a linear program. The goal programming component refers to the fact that constraints are formulated as soft constraints instead of hard constraints, and that helps minimize infeasibilities in the solution. And then the preemptive component, again, refers to this idea of priority levels. In the optimization, this means that no high priority policies are sacrificed for low priority objectives. So a little bit more about how that works. RiverWare optimization is a global solution, whereas the rule-based simulation solves time step by time step, object by object. The optimization solves all objects and all time steps simultaneously. Now the policy is formulated as a set of prioritized goals, where the goals once again use the same RiverWare policy language, and each goal contains either a set of soft constraints or a traditional objective function to minimize or maximize an objective. When the goal contains soft constraints, then RiverWare converts that into a derived objective where it defines a satisfaction variable, and then the objective maximizes that satisfaction. Then RiverWare solves a linear program at each priority level, and once it solves, then it locks in or freezes the objective value. And in that way, a lower priority objective is not going to degrade a higher priority objective or policy. And then if it comes to a priority where it cannot fully satisfy all of the soft constraints at that level, then it's going to get as close as possible. And so again, this use of soft constraints minimizes infeasibilities in the solution. So the optimization solver is used by Bonneville Power Administration for managing hydropower in the Columbia River Basin, which is in the northwestern United States. In the entire basin, there are over 30 hydropower dams that are managed by Bonneville, but they focus mainly on the 10 largest, which they refer to as the Big 10 system. The system as a whole has roughly 1/5 of the total US hydropower production. And as with most river basins, there are many competing objectives in the basin. So a key one is environmental objectives, primarily for fish protection. Salmon is a critical fish species for economic purposes, cultural purposes, also for the ecosystem. And so there's a wide range of very high profile requirements, complex flow restrictions that apply for different seasons to protect salmon spawning and juvenile salmon migration back downstream to the ocean. So they have to account for all of those in their modeling. And then in terms of power production, they're looking to meet local power demand, but they're also participating in power markets with their surplus generation. And then another key is there's a lot of wind generation in the region, so they have to maintain sufficient reserves in their hydropower system to be able to balance that variability in wind generation. So multiple groups at BPA use RiverWare, but we'll focus on the short-term planning group, which uses the optimization for managing the Big 10 system. And this group is typically looking out 2 to 3 weeks at an hourly time step, and they're using the model primarily to guide day-ahead marketing decisions. So a key output from the model is how much power should they buy or sell on any given day. And they're doing this not just to maximize their hydropower revenue, but they also need to keep their system well positioned to meet constraints. So make sure their generation is going to match up with their water demands while they're meeting their local load. And so at the top of the system, upstream, they have a very large reservoir, Grand Coulee, which has seasonal storage and their largest generating capacity. But downstream of Grand Coulee, all the reservoirs are relatively small. So it's essentially a run-of-river system at a daily time scale. And there's about a 1-day time lag from the top of the system to the bottom. But it's down at the bottom where most of those strict flow requirements apply. So they have to make sure when they're operating Grand Coulee for their power objectives today that they're not going to create trouble in meeting their flow constraints at the downstream end tomorrow. And so that's really where that global solution and optimizing the system together becomes critical, and looking at all of those system effects simultaneously. And just to wrap up, to give a sense of where RiverWare fits in hydropower management in the US, you can see here that roughly 1/3 of the hydropower in the US uses RiverWare optimization as part of its hydropower management. In addition, there are dozens of bases that are using rule-based simulation. So RiverWare really plays a critical role in the multi-objective management of water and hydropower production across the US, and increasingly in countries outside of the US as well. So that's all. I thank you for your time, and I think maybe we have time for a few questions.
Thank you, Mitch. Yes, we have time for a few questions, in fact.
A very short question, if I may, please. Mitch, I'm not quite familiar with the geography in the US, sorry, but I guess you said that one of those basins, for example, goes up to Mexico, right? Flows down to Mexico. So just a general question, and I know you are not a politician, neither am I, but how relevant is Mexico in decision making, for example, for what you do in the upstream? My question is because sometimes when there's relationship between one country and another, there's always one country which dominates, as it happens to us, for example.
Yeah, so through most of the 20th century, it was mostly unilateral decisions where the US made decisions and Mexico was kind of left with what was provided. The one requirement is the US had to provide 1.5 million acre feet of water annually to Mexico, and there were also salinity levels that are within that treaty that they had to meet. But in the last couple of decades, there has been a significant shift where now Mexico actually has a more active participation in the management decisions, has options now with recent minutes or updates to the treaty, where now they have the opportunity to store water upstream in the basin for later use, and then have an active participation in surpluses and how shortages are allocated throughout the basin. So it really has been a change in recent years to where now there is more of a bilateral management of the basin.
Thanks, Mitch.
Few more questions.
May I just raise a quick one? So Mitch, you said that you used the code programming, and what kind of code programming formulation you used? Is it weighted sum or?
It depends. So the key, there's two pieces. It's the preemptive goal programming. So it differs from a traditional goal program where you might combine all of your soft constraints in a single objective. They're really separated out at different priority levels. Within those priority levels, when you're trying to maximize the satisfaction of the soft constraints, there's actually 4 different approaches that you can use in RiverWare. One is just a basic summation approach where you're maximizing the total satisfaction of all the constraints at that priority. There's a maximum approach where you are maximizing the worst satisfaction, or you could say minimizing the worst violation. And then the 2 most common is one we call a repeated minimax, where you minimize the largest violation, then you do that repeatedly until you've done the best you can with all violations. And then the last one is a summation that uses a reward function, and that would be maybe the closest to what you're describing, where you can apply either a weighting or a specific function to the violations. One way that's commonly used is basically the equivalent of minimizing the sum of squared violations, but you can in general apply any reward or penalty function to that.
So some kind of priority or the weights as a base. Yeah.
Yeah. So that weighting would be within a single priority level, and then each of the individual priorities are distinct.
Okay. I just noted that did you use the augmentation terms to ensure that part of the optimality or not? Because in Go programming, so we need to use some augmentation terms. Otherwise, so the solution might be weakly Pareto optimal. So it means that in some objectives, still we can improvement without sacrificing in others, just a note. So if you didn't use some so-called augmentation terms formulation, which is a terms that add very small tips to just ensure the Pareto optimality.
I'm sorry, I'm afraid we have to stop the session here, but I encourage you to continue through the chat and to continue this discussion, because we have the following session that is already starting. So I would like to thank you, Mitch, and all the participants. It was very interesting.